Hi everyone. I'm going to be doing a quick walkthrough in the coding portion of this week. I did not provide. Oh, sorry. Wow. I did not provide. I did not provide a markdown for you this week. We're just going to run it through the code, and you're going to produce an R markdown as part of your assignment. And I'm just going to walk you through how to load in imagery bands, and these data are provided for you in the week 6 module. I'm going through band combinations, how to calculate NDVI, how to calculate an unsupervised classification. And right now the code might look pretty intense, but when you break it down, it's not so bad. Or you might say that looks pretty easy and great for you. So I'm just going to walk you through what I would do for, a couple different ways of going about this and how I would structure my code. So right now my environments are empty, my console's empty, so we're just going to be doing it one code at a time. So also one thing I've seen is I've met with some people, some people are clicking on a line and coming up here and hitting run. That is a great way to do things. You can also just highlight over it or click on the line. Right now I'm on line 8. And if you're on Windows, you can hit Control Enter, and it will run the line for you. If you're on Mac, you can hit Command Enter or Command Return, whatever it is. I don't understand Macs. It's funny. Like I'm like I'll have an iPhone. iPhones are great, but if it comes to Macs, I'm like ugh. So like I don't know. I don't get it. But that's what it is. So I'm going to load in my path to my Landsat data. This will be different for you, but right now it's sitting in Denethor, NR6950, data intro to RS, Landsat 8 imagery. So that's my pathway. I'm going to load in my libraries. If you remember, we did a projection in week 5, and this is Albert's equal area of NAD 83. This is like my preferred projection. I just like it. So I'm going to load in that information, and you can find this information online for every single one, right? Now I'm going to set my working directory. We have covered this, I believe. If we haven't, a working directory is just as it sounds. So it assigns a folder of data and says that this is the directory we're going to work in. I have a path to my Landsat data, and I'm going to set my working directory as that path, right? So now if I run the function list files, I'm going to list all the files within that working directory. Pops out down here. I got 7 bands, right? 7 bands of Landsat data. And this is the data I'm going to work with. So it's just a great way to set up your stuff, set a working directory, and look at what you have. So now I'm going to show you how to load the imagery. And so each band is a TIFF file, right? Band 1 through 7. That is my wife, and I always have Christmas as my... Sorry about that. My wife called, and I will always answer the phone. So this is one way you can load in each band or TIFF file one by one. So I can assign them to B1 through B7, and I can just do ba, 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 ba. Now I have my 7 bands. They are unique, and they are according to each band, right? And then I can stack them using concatenate and create a raster stack because they're all the same spatial resolution. They're all the same spatial extent. And so I can run L8, L8, I just, Landsat 8. And I can look at L8. And now I have a spat raster because we're using Terra. I have the dimensions of 8001 pixels by 7871 pixels in 7 layers, so 7 bands. They have a resolution of 30 meters. They have a coordinate system of WGS 84, UTM zone 13 north, EPSG code 32613, and then their names. So that's one way if you want to do things. it's a lot. So I go about it a couple different ways. So now I have, I can do list files, right? Because I have my path equals path Landsat, so it's directing me to my folder that has this data. And I can do even a pattern search. So I only want to search patterns that have a .tif associated with them, because they're all .tif files. And then I can put a $sign after that, meaning I just want to search for this, right? I can do a pattern, and I can just call that files. So if I run 37, I now have files. And if I run just files, look, my listed files that are all .tifs. So my 7 bands. Now I can concatenate these files, and then I can make them into rasters as such, and I can view them, and I have the same information I obtained by loading them in one by one in a couple of lines much quicker. So listing the files, concatenating those files, turning them all into rasters, and they're already concatenated, so it's a raster stack. You could also do a for loop. It's basically the same thing. There's not much difference. You can add in extra things if you wanted to do projections, things like that. So for loops are important, and they do have their purpose. They can be very useful if you're loading in a lot of stuff and you have a lot of processes to run through just to get your imagery set how you want it to be. For this, it's pretty much the same as the method right here of listing files and stacking. So I can do files again. It's the same exact function where I'm just identifying my files. If I run that, there's my files. And I can do a for loop. So for I, and this I could be anything. I could put it as, X, Z, whatever I wanted to. So for I in files, so for a given number in my files, so one of these 7, I want to take all these files and stack them, and then I want to assign them to L8, and I want to rasterize all of them. So I can just hit for loop, and then boom, and it's the same exact thing once again. So this is just 3 different ways. You might feel more comfortable at the beginning to just load them in one by one so you can get to know them a bit better. Or you can start getting into quicker ways if you're doing a lot of different data sets. I highly recommend using a for loop or just listing the files as such. There's a couple different ways to do this that I haven't provided to, so you might have a different option. But that's how you could load in your imagery data and stack it into one specific spat raster with 7 layers. Perfect. So let's plot these layers. Let's see what that looks like. Don't worry about the errors. I don't know why I had so many errors. But if you plot the bands, right, they don't look like anything special. And it's like kind of even difficult to understand what's going on here, which is fine. It's putting these bands together that we're actually going to see something, right? So right now we are in, this imagery covers parts of Colorado. And I am going to add in the data of the specific area that I provided in the data sets, where we're going to subset this to a specific county. So DECO, you'll see, stands for Delta County. This is Colorado. I've provided the counties data set, so if you plotted this, you would see all the counties in the United States. We're going to be using some of our skills that we acquired earlier on in the semester to filter them to a specific geoid. Now, there's like 3 delta counties, and they're fairly close to each other, but we only want a specific delta county. So I found the specific geoid value that is in this data set to narrow it down to the specific delta county. So I'm just going to filter. Since this code is provided for you, you don't need to go searching for it. I am going to transform this data into the same data of my imagery. and I'm going to make it into a spat vector because some analyses require a spat vector if you're working with spat rasters. I am going to plot now Delta County. So this is the extent of Delta County. This is what it looks like. So now I am going to crop my Landsat 8 images, and I'm going to mask them. So I've cropped them to about this spatial extent and one big rectangle around it, and then I'm masking it so it takes in the specific geometry of that county. And now I'm going to plot my newly acquired imagery. So these are the 7 image bands that we loaded in earlier, and they are cropped and masked to Delta County, which is pretty awesome. It works just like the raster data we worked with in week 5. So getting into band combinations, we covered this in lecture. If you haven't watched the lecture, it'd probably be more useful to do that if you don't know remote sensing. If you do know a lot about remote sensing, then please continue. So we are going to create Landsat band combinations to get, different images that capture different spectral properties of that image. So here are some of the combinations I provided for you. Natural color, false color, color infrared, agriculture, atmospheric penetration, shortwave infrared, vegetation analysis, things like that. So we're going to be using the plot RGB function, which is right here in line 90, and then again for like 8 different times. But first, before you run plot RGB, you need to take 3 specific bands and put them in a specific order. So I'm going to call this Landsat Nat. So Landsat Natural. I want a natural color image. So 432, right? That's the combination for natural color. So I am going to run my L8C, which we created here. This is the masked images. So we have these 7 bands that are masked. L8_C, and I'm going to put 2 square brackets. Now 2 square brackets will go in and identify which one out of the 7 I need. If you just do 1 square bracket, it won't identify to the specific band, but the names. So we are looking for a specific band of 4, then we're looking for the specific band of 3, and the specific band of 2, and we put them in that order. So L8_C, 2 square brackets, 4, 3, 2, in that order, and so they're assigned to Landsat Nat. Perfect. So now if we run this, you'll see it is a spat raster of the resolution, or the dimensions, the resolution, but of 3 bands. Bands 4, bands 3, and bands 2. So it's basically just subsetting from our 7 bands, right? We're just subsetting to these 3. Now, in 90, we're going to run plot RGB. So we've already established what we want as our 3 bands in Landsat Nat, and we're going to provide a stretch. So stretch is just a way to modify the way the image looks visually. We're going to do stretch linear for all of this analyses today. So if you do Terra plot RGB, provide your 3 combination band combination, so Landsat Nat, provide the stretch, and plot it. Boom! We now have an image that has been cropped to Delta County, and it's a natural color image. This is what it would look like if you were, flying over the Earth. You have your bare ground, you have your vegetation, you have clouds. It's a little darker in some regions. But there you go. This is a natural color image. So pretty sweet stuff. And that's just from one combination. Now we're going to be running through the rest of these, and I'm just going to run through them quicker. This is a false color urban, so 764. Let's plot it. Boom. This can be useful for urban areas. It'll give it into a false color that you'll be able to see a bit more into the gray. It distinguishes a bit more between bare earth, soils, and vegetation for sure. You can see this is much greener. You can see that this is much more gray, and it's much more appropriate for large urban areas. So now we're going to do color infrared for vegetation, false color, of 543, and we're going to plot that. Boom. So now this is very useful for discriminating vegetation. This is showing 543. So band 5 in Landsat is near infrared. 4 is the red band. And so we are showing that vegetation in red. It's really helpful to discriminate among vegetation. You'll see here it's bare earth, you have your croplands, you have some riparian vegetation coming through here, and then you have your forests. So this is really useful in using vegetation. So vegetation study, it's very common color infrared. Agriculture, this is 652, and if you plot it, vegetation turns very green. It's very similar to the false color urban. And that agriculture has just this bright green. Now, all the vegetation up here in the mountains, like the forest, definitely turns green as well because they're both vegetation. But it has its use in agricultural studies. Atmospheric penetration. This is part of one of the questions on the quiz, so I'm not going to cover it here. I'm going to make you Google it. And then, but you can see vegetation turns light blue, and the rest is kind of this greenish, grayish, yellowish property. So now we're going into land water. So this is very useful for discriminating land against water. The next one is shortwave infrared 754. You can see that this is also very useful for picking up vegetation. Vegetation analysis of 644, which is interesting. That should not be it. It's 654. So you're going to have to change this in your own code. I didn't catch it till now. Boom. Same kind of thing. It changed very little. Focus on this area right here. When I go back, you can see that there's just very little change. A lot of these band combinations cover very similar things. And this is just for fun, 572. I like just looking at it because it's just cool looking. So, you can mess around with different bands to create different images. So, let's say we want to do I want to do band 3, band 7, band 2. Let's see what happens. Not that exciting. Let's do band 3, band 7, band 5. Ooh, very pretty. Let's do band 6, 7, 5. Yeah, But you can play around with your different bands and see what might be useful for a specific analysis. It doesn't have to be one of these defined ones. You can figure out something that works for you. But now you know how to create band combinations. So you just define a variable, and from your stack of rasters, you define which 3 in which order you'd like them to be. Use plot RGB to plot that variable, and use a stretch of linear. I'm just going to show you what happens if you don't do a linear stretch. So this is our natural color. Much darker, much less defined, not so good. Let's take a look at it again with the stretch. Much better. So stretch linear helps. Now, these specific bands 1 through 7 have names because they capture different portions of the electromagnetic spectrum. So this is the ultra blue light, green, red, near infrared, shortwave infrared, and shortwave infrared 1 and 2. So we're just going to assign the L8 underscore C a set of names. And if we ran L8C, we can see down here that now we have given each particular layer a name. This is just one way to do it. Names, put in your Landsat or whatever, satellite imagery, or stack. This could be any type of raster stack. Put in the concatenate function, and then put in the names according to the layers. So 7 names, 7 layers. Moving on to NDVI, so the Normalized Difference Vegetation Index. Remember from our lecture, this produces the measure of greenness across the landscape. So the NDVI formula I've put into a function. Feel free to use this function, but I would suggest that you do not just copy and paste it. You write it out yourself so you can just get to know it a little bit better. So this function, I'm creating a new function called NDVI formula, and I'm putting in the function, as we learned how to do functions. Imagery, red band, near infrared band, right? So I'm assigning the near infrared band. My image is fifth band, so this would be L8C, L8 underscore C5, so the fifth band, near infrared. R stands for red. This is my image, so L8 underscore C, and I'm directing it to the fourth band, which is the red band, as we can see right here, near infrared, red, so 5 and 4. Then I'm putting in my formula, which we learned in lecture. VI, vegetation index, stands for the near infrared minus the red, divided by the near infrared plus the red. And I'm returning that function. So all I need to do is put in my image stack, so my raster stack, and then I need to have, I don't need to do anything. That's it. So I'm going to run that for you. You should run it with me because you're probably following along, and if you aren't, you probably should. So I have created the NDVI formula function. It's right here. I just need to put in my imagery. And so what is important is if you only had your near infrared and red, you would change this to 1 or 2, depending on where they sit. But since we have the 7 bands and they're in order, we can use the 5 and the 4 because that's where they're located. So calling it NDVI, I'm going to run it. Perfect. And now I've created an NDVI for this extent. So I'm going to 135 and I'm going to plot it. Whoa, pretty awesome. So we now have a NDVI output, so the measure of greenness for our landscape. And you can see how this plays into the vegetation and the land around it. So some crops are very green, they're probably getting a lot of water, probably very healthy. And then you have your forest up here, which is very green and most likely conifers, so they're green all the time anyway. Then you have your clouds, where you're not getting any greenness through it. So that's our output. I'm going to put the little boundary around it. Nice little boundary. But pretty sweet. That is our NDVI image. It is done through this formula, done through the near infrared and red bands, and that's the output. So we can also plot with terrain colors. So we can use the rev function and put in terrain colors function to plot. So right now it's on this continuous scale. So if we wanted, we could change it to, I want, 10 specific colors. So I'm going to run 138. Now it's broken down into 10 specific colors. I could say I only want 3 colors. Run it again. Now it's just broken into 3 distinct colors. So this is just one way you can modify what colors you're viewing, if they're on a continuous spectrum or they're broken down into like classes. I prefer the simple NDVI output. I think it's the most helpful. So NDVI, I don't know if I mentioned this, and which would be silly if I didn't. NDVI is measured from -1 to 1. So 1 being the highest amount of green possible. Here we don't even have measurements into the 1. And then we have measurements down to about -0.1. So that is our scale of greenness, but ideally, in reality, it can go from 1 to -1. But great. You can see which areas are greener, which areas may be more healthy, but mostly it just measures greenness. So let's say we want to use this greenness, right, on a different image. So we can use what's called the clamp function here in 144. And essentially we can mask out certain portions based on their values of rasters. So in 144, if you see, I'm assigning a function or a variable called veg. I'm going to use the clamp function, and I'm going to use it on my newly created NDVI output. So basically what I'm saying is I'm going to mask out every value that is either 0.3 or greater. So if you look over here, 0.3 or greater. And you put values equals false. It's just part of it. It's a threshold. And I'm going to extract those values. So if you run 144, and if you run 145, which would be to plot just that clamped data, so everything above the 0.3, assign it the color green, and you'll see now I have just selected everything above 0.3, which is pretty cool. It's just a way to extract information. And so that could be used for anything. You could do that with elevations. Any value a raster has, you can use CLAMP to extract certain values. We can plan or plot our boundary around it, so you can kind of get a good idea for Delta County where your green vegetation is, which, you know, could be very helpful if creating like a land cover map, anything like that. But the 0.3 was subjective. I could change that to, 0.1, get in bare land because it's technically not vegetation, but it has an NDVI value. So what we could do is we could plot our Landsat natural like we did earlier, and then we could plot over our vegetation on it. Boundary. Pretty cool. So, I mean, that's one way how this could be useful. You can see that it's not picking up some vegetation, right? There, you can see there's some vegetation, but it must have been under that 0.3 threshold. So that's called thresholding data. You can do it with the CLAMP function, and you can extract different things. This is pretty, I think, pretty awesome for vegetation analysis. So now that we've created our NDVI, I'm going to plot that again real quick. Right? What happens if I plot over that vegetation? Where is it? Oh, that's pretty gnarly looking. All right. All right, goodbye. So now that we've created our NDVI, we can get into unsupervised classification. So we're actually going to change locations. We're going to Deer Lodge County. If you don't know where Deer Lodge County is, look it up. So using the Deer Lodge shapefile and the Deer Lodge Landsat 8 TIFF provided in the data folder, load. We're going to plot those real quick. So I'm going to plot band 1. So this is the cropped extent of Deer Lodge County. And there's Deer Lodge County. Pretty sweet. Good looking county. So we're going to do our quick NDVI formula here again. It's already loaded if you keep going, but it's just another way we can load it. Same way before. And we're going to assign NDVA underscore L8 to the NDVI formula, which we've created here, to our Deer Lodge Landsat 8 data, which has 7 bands of Deer Lodge County. We ran our NDVI and we're going to plot it. That is the extent of Deer Lodge County, but our NDVI across the landscape. Right off the bat, you can see a couple of things. You can see your crops, right? You can see which areas they're really selecting for water use, so they're trying to grow. You can see what would be forests, some riparian areas. It looks like down here. This would be probably mountaintops because it's rocky and there's no vegetation, so you're getting that kind of zero output. It's not green at all. And you can kind of see where you'd have some bare land, and probably you see a little line here, probably a highway coming through. So very cool. Now let's we're going to be doing right here in one. I'm going to move that down to 177 now, which could get confusing. So make unsupervised classification if you're following along on line 177 by hitting a couple of returns here. And we are going to assign our values of NDVI-L8, this here, so these values, to NR. We're just going to call it NR. So set seed. Set seed is a function. It's part of your quiz today, or this week. So I'm not going to tell you exactly what it does. You're going to look that up yourself. But basically, it's a way to have reproducibility in statistical studies and things like that. So you can set a number. I just put 100. Set seed. Now we're going to be using the k-means function. So as you remember from our lecture, k-means is just a clustering method for clustering information, in this case NDVI values, to provide specific classes of land cover. So we run the NAOMIT on NR. This provides, if we have any null values, we're getting rid of them. And so there's a lot of rows here. and that's a lot of information we don't need. There could be some null values in here which we don't want to use. So we're just going to run the NR or NA omit over NR. Centers. Centers stands for how many clusters we want. So basically, how many different classifications of land cover on this landscape do we want to provide? In this case, I just want to do 5. I want to have 5 distinct classes. Iteration max, so how many times k-means will run its functions. I'm going to put 1,000. You can change this number around. It's kind of fine-tuning your function, but for now, 1,000 is fine. End start, we're going to have 5 random sets, and we're going to be using the Lloyd algorithm. And so to use k-means, you honestly don't need to understand everything that's going behind it. As long as you understand, I want to create 5 clusters, I want to make it run 1,000 times, I want 5 random sets, and I'm using this specific method, that's what, you can run it. And so that's the great thing about being an analyst, is the statisticians and the computer programmers, they can do it for you, and you can use their tools. But the more you get into things, you can get to know them. But right now we're just basically creating 5 different classes across the landscape of land cover. So we're going to assign that to a vector, or variable km. So k means n cluster, right? Run that there. Depending on your computer, this might take a while. I'm expecting it to be done fairly soon. But I've been wrong before. Done. So that took maybe, 10 seconds? So now I'm going to use the str function to look at its structure. So it is a cluster, and so the k-means function provided a lot of information. Basically, we are going to be looking at the cluster. So you can see 4, 4, 1, 2, 1, 1. These are basically between our 1 to 5 classes for this many values. So we have created from this many distinct pixels to 5 different classes. So what we're going to do is we're assigning a new function, knr, to our ndvi, right? And we're going to want the values of this image to reflect the values of the clusters that we have here. So values of knr, which is assigned to our ndvi, we want to choose the k-means cluster in the cluster section. So this right here. Basically, we're saying we want to have our ndvi image, but we want to change its values from all of these possible pixel values to 5 specific clusters that we created in k-means. So we can view now knr, which is the new ndvi with the new values, right? So now we have a spat raster, we have 1 layer, and we are ready to plot. So if I went down to 201 and I hit Terra plot, I want to plot the knr, I want to call it unsupervised classification. If I got rid of this color of my colors, this is the basic default. This is what it looks like. Boom. So between like a salmon color and a dark green color, we now have 5 classes across our landscape. So this could be helpful. You can kind of see how things work. You have that darker green, which may be forest vegetation. You have that lighter green, which could be grasslands, prairie, sagebrush, I don't know. And then you have this area which is more bare earth. You have your agricultural land. You have your rocky outcrops. So, I mean, the general colors that pop out, they could be helpful in understanding classifications across the landscape, but I'm going to give them colors. So, in 198, I'm providing a set of colors. And so, honestly, there are so many different colors. I'm providing a couple different ones in the resources for Module 6, but basically I'm assigning classes 1 through 5 different colors: gray, Dodger blue. You'll see what hashtag DAA520 is. Green and wheat in color. So I'm going to run 198, and now I have 5 classes and 5 colors, so I can put in my plotting function color equals my color, which is this. So I can plot knr, unsupervised classification is my title. I'm giving it a color. Type is classes. This is very important because we're plotting specific classes, not a continuous scale of color. and x is equal false. I don't want anything around it. I just want the image. So now I'm going to plot it with that my color. You can see how things change a little bit. Can see how things change a bit. There we go. So right now, these are just colors I chose. You can change them up. They might not be helpful for you, but I'm looking at gray as kind of bare earth. That wheat tan color is like agriculture. Kind of this scrubby vegetation is brown. The dark or the light green is forest vegetation, and the blue is water or ice. And so these are actually snow-covered peaks, right? And we're going to look at that. And this is water, this is agriculture, and this is like rocky outcrops and forests. So right now we have our classification. We're going to run a natural color composite, and we're going to plot it of this area. We're going to kind of take a look at how they look. So this is the real image. Well, reality is relative, but this is our natural color composite. So if you look up here, you'll see our vegetation. Underneath it, you'll see this is the town. This is some water. These are snow-covered peaks. This is darker vegetation. This is pretty much bare earth. You have a road coming through there. You have some riparian. And we have some clouds. So how does that match up with our classification? There we go. So, I mean, pretty good. You can see we're classifying the image based on NDVI values. So the more classes you could do, the more it would look crazier, the less classes you could do. We're going to be going into supervised classification later on in the semester, so we're going to actually be assigning classes based on spectral values to get a little bit better of a classification. But based on k-means and just running a function, this actually does pretty well for classifying different land cover. And you can change this around, you can change the colors, you can change the number of classes you'd like in that k-means function with centers. But right now, that's not bad. So let's mask over the county, and we're going to plot that again with our county polygon outline. Let's see if that runs. So not bad for Deer Lodge County. Pretty good land cover, classification. And that is unsupervised classification. It is probably the simplest classification you'll do for remote sensing data. But now you can break it up into different classes. And this could be helpful for a number of reasons. And so we could even clamp out specific classes now too, using our thresholding methods. So that was a brief introduction to bringing in satellite imagery, stacking it, subsetting it to a specific area, doing band combinations, running NDVI, thresholding data and using the clamp function, doing an unsupervised classification, changing colors, and plotting. So I hope that was helpful, and this is kind of your, this would be like work time where you get to understand the function, the functions that were provided, and then you will be doing a very similar analysis for your week 6 coding assignment. So I would refer to this script as it will help you move forward. And hopefully by the end of this week, you now can understand the basics of remote sensing, and you can load imagery, you can work with imagery, you can stack it, you can modify it, crop it, project it, and you can calculate NDVI and an unsupervised classification. So not bad for 1 week. It's good stuff. If you have any questions, please email me. I hope you guys have fun and enjoy the remote sensing portion of this course.